All right. Good afternoon, everyone. So let's begin with or continue with our exercise today. So basically we had just created our clusters. We decided to go with 2 clusters. And we were just about to explore what those clusters look like. And so if I have this correctly, I think we stopped on this chunk here, zone DF, is that right? Okay, so on my side, my environment is empty, so I'm just gonna go ahead and run all above, except that I want to just make sure that chunk that takes a long time is commented off so it doesn't run, which was this chunk here. So I'm going to just comment this chunk off so I can run all above. And then we can continue. If you're also doing the same as me, make sure you do comment this chunk off again. Just want to say that because if you don't, it's going to try to run and then it takes a while for that to go through. So once I have that commented off, I'm just going to come to the exploring clusters heading 1 in our table of contents, and I'm going to run all above. So if y'all just to kind of recap, so we talked about a few different ways of checking what's the best number of clusters for k-means. And then I showed you the function, the one that I commented off, that basically uses 26 different indices of similarity or dissimilarity to provide us with a vote on what's the best number of clusters. And for this data set here, that the number of clusters that received the most vote was 2. So then we decided to continue with 2 clusters as our decision here. And now, so after doing that, we stopped at this chunk here where we're going to basically prepare our data set to explore those clusters and really start understanding what are they and what do they mean for our data set. So in this next part of the chunk, I basically want to start off with our data set that we use to create the clusters, which is, so if you give the assignment symbol, we're going to start off with all underscore v underscore n. I just want to print that so you can see what that is. That has all of the rows of our data frame that remember this was the data frame that had no NAs, right? So we dropped an A because the k-means algorithm does not handle NAs. So we dropped all NAs and we also standardized the variables. So they are ranging from -1 to 1, or not -1 to 1. They're centered around 0, but ranging from -3 to +3, or some range like that, depending on the variability. So that's what we're starting with. So my goal then is to add a column here that would be cluster ID. So if we give the assignment or sorry, not the assignment, but the pipe, and we come after the comment here, let's use a mutate, and I want to call this as cluster, this next column. So really the cluster ID or the cluster assignment is in the object that we created our last k-means model. So that object we created here on the mod km2 with k equals 2. So mod underscore km2, if we use the $, we can get inside of its components. One of its components is cluster. So if I just print mod km2 cluster, it's basically the cluster ID for all of our observations. So if you just run that and you print zone DF, you're going to see that we have this column now that's called cluster, and it has the numbers 1 or 2, because again, we chose k equals 2, so we have 2 clusters. It is interpreted by R as an integer or numerical variable. and I want to change that to be seen as a factor. So we can just plug this into an XMutate, and I want to overwrite on this column. So I want to again call it cluster. And really, we're just going to call the function factor on the current column cluster. So we're taking the factor of cluster and rewriting that again on a column called cluster. So we're overriding that numerical cluster with a categorical one. If you run that and you print it, now we have that cluster column with ones and twos, but now seen as a factor, so as a categorical variable rather than a numerical one. All right, so one thing that we could potentially check here is how many observations do we have per cluster? Just a very quick EDA, just to have a better idea of how many cells of all of this whole field were classified as cluster 1 and cluster 2. How would you do that? If I start off with zone F, I will give you a pipe, and then what function do we need here? Or what's the next function we need here for this? So we already have the clusters as a category in this column cluster. Now my goal is to know how many of our observations were classified as cluster 1 and how many as cluster 2. Anyone in Tifton wants to give a suggestion? Okay, so Amandeep said, let's group by cluster. That's the next step here. So group by our column cluster. And then if I want to know the number of observations. So there's a couple different ways, but the most efficient one is to use the function called tally. That basically just gives us the number of observations. So if we run that, we see that we have, at least on my side, on yours a little bit different, most likely. I have about half of the observations almost on cluster 1 and the other half on cluster 2, which is interesting because it doesn't have to be that way, right? We could have 2 clusters and one of the clusters have the majority of the observations, like 70%, 80% of the observations. So the fact that they're kind of like almost evenly split is perhaps a good sign, I guess. We'll see once we plot it. All right, so on the next chunk here, my goal is to make a quick map so we can actually visualize how this looks in space. So let's come here, start calling our ggplot. Let's give it a plus. So imagine now that my goal is going to be to make a map, the same map of the field that we've had, but now I want to color the polygons, the mini polygons, the cells by cluster. So I want your help here to help me develop this code. So I gave you the ggplot. Now, let me see. Marco and Tifton, what do you think? What is the next function we need here to make that plot?
geom_sf.
geom_sf, perfect. What would you type here?
AES,
Okay.
and then cluster. Color equal cluster.
Awesome. So this is going to be the fill, but I like what you're thinking. So fill equals cluster. And I do want to say color equals NA. So if y'all remember, if we leave color is, in this case, color is just the outline of the boundary of each one of the cells, which just adds some noise, some visual noise. So by removing it, we can see better the actual data behind it. I think we're missing something here for this to work. Anyone has any thoughts?
The data.
The data, right? So where
Yeah.
would you put the data and how would you do it?
Your main safe before AES, you put data equals
So we're gonna use the zone underscore df. That's the one we just created above. Yeah, perfect. Thanks, Polly. Thanks, Marco. All right, if we run that, this is how it looks like, at least to me. On your side, it may look a little bit different. So I guess a couple of things I want to mention here. On your side, it may look a little bit different for two reasons. The first reason is that you may have just a slightly different pattern just because, again, our boundaries were different, our grid is different, our interpolation is a little bit different because all of that. So overall, you may have a little bit of a different pattern, but still you should be seeing something like this. Another thing that could be causing differences on your side from what you're seeing on mine is that k-means, because k-means has a random starting point, that random starting point, although in the end you may get to the same cluster if you run it multiple times, but even on my computer, if I rerun it, it's possible that then my cluster one is actually flipped. So if you think of colors, it's like if you flip colors. So if my left side would have been red and my right side would have been blue, it could have happened that. So it could be that you end up with the same separation, but in one computer, they call cluster one what's on the left and cluster two what's on the right. And in another computer, it may call inverted. So two on the left, one on the right. It could be due to that. But overall, you should be seeing a similar pattern, somewhat of a similar pattern to what I'm seeing here. Okay, so I do want to make some very specific changes to this plot because this will come down to an assignment that will follow this exercise. So a couple of things I want to change here. The first one is I want to change to a colorblind safe friendly color scale. So let's use scale underscore fill underscore colorblind. This is a new one. We've been using varieties up until now. Scale fill colorblind is a new one. So it's going to be a black and yellow type of color. I do want to also change the title of this plot. So if I want to change the title that's in the labs function, we say title. I want to call this, and I want you to call this as well on your side, because again, this is going to be part of an assignment that is important to make this change. I want to give a title of unsmoothed there we go. Unsmoothed zones. This is the title I want to give it. So if you just run it, you should see something like this. Also, we're going to use theme map. So theme underscore map, just to make it a little bit more clean for us. And lastly, I just want to make some changes to this title. So I want to change the color and also, no, that's it. I just want to change the color. That's all I want to do. So if I add a plus, if you remember, every time we want to change something very specific about the theme, we need to call the function theme. And here there are many arguments. The one we want to change is called plot.title. Because the title is a text element, we need to call a function element text. And then say color equals, I want this to be equal to blue. So this is how it should look like on your side. And now lastly, let's export this to file. So let's call ggsave. I want to get outside of code, go inside of output. I want to call this zone underscore or zones underscore unsmooth dot png. Excuse me, pollen allergies. I want the width of this plot here to be equals to 3 and the height to be equals to 4. And these units are in inch, or these numbers are in inches. So if you run that, go on your files tab, go on output, you should see now this plot just like this. So before we keep moving and talking about the next step here, I just want to, open up and check if anyone has like a very different looking map. I don't expect it, but you never know. Perhaps did anyone have the colors flipped compared to mine?
Yes.
I did, yeah.
Okay, perfect. Yeah, so that is completely fine. There's going to be a point on this exercise that will make a difference. That for me, cluster 1 is the black one on the right, and cluster 2 is the yellow on the left. So there's going to be a point that we're going to give names to these clusters. We're going to give context. So we're going to say cluster 1 is high yielding, cluster 2 is low yielding, or the other way around. So whenever we get to that point, make sure that you answer that based on your map and not mine. Okay, so basically we just ran one management zone exercise using k-means and soil terrain and electroconductivity variables. Again, we could have done this using different data layers, right? We could have brought perhaps soil nutrient data if we had soil pH, perhaps if we had some type of like nematode count in the soil, if that was important for this field, that could have been brought here as well. We could have brought remote sensing data, so maybe imagery, both of bare soil and also crop. So there's a lot of other layers that we could have brought into here. And not just the layers, we could have also used other algorithms to create these zones, right? So we use k-means. There's other algorithms. One very common in precision ag is called fuzzy k-means, which is a pretty similar approach to k-means. It just, the way that assigns membership to different clusters is a little bit different, but overall is very similar. But there are other ways, other algorithms we could have used here as well. So just wanted to make that clear that this is not the only way of doing management zone. Obviously, there's different ways. All right, so looking at this map, you may notice that there's some speckles, right? There are some speckles of one zone inside of the other. What I mean by that is, let's say in the middle of all black points, you have some speckles of yellow. And in the middle of mostly yellow points, you have some speckles of black. While that is just part of the exercise of the management zone creation itself, because if you stop for a moment to think about it, we did not give k-means the geographical location. K-means does not know which cell is neighboring which other cell. For k-means, these are just rows of a data frame. So k-means is in this case that we are using here, k-means is completely unaware of the spatial context, which is still very interesting to think about it, because even though k-means has no knowledge of the spatial context, we're still able to create two zones that, for the most part, are pretty contiguous, right? It's not like it's all a mix of yellow and black everywhere. Like we clearly see there are two halves here, one mostly yellow, one mostly black. And that is pretty much because of the inherent relationship and correlation of the data itself, right? So even though we did not tell k-means, hey, this is the x coordinates, this is the y coordinates, take that into account, k-means is still found somewhat compact clusters or zones because the data that we use for creating the zones is inherently dependent in space, right? We know that in precision ag, things that are closer in space are more correlated than things that are farther away in space. So that is just basically why we have these clusters that for the most part are pretty cohesive and not just a complete mix of unstructured black and yellow everywhere. However, we still have this speckling effect that I was telling you about. And even though this is just part of the result of this analysis, but for a grower that is managing whatever we want to manage with the zones in this field, it's probably not gonna be very feasible for them to be. So let's say that at some point we determine that my zone 2 here, so the yellow zone is gonna get X amounts of an input, and the black zone is gonna get half of that. If we determine that at some point, it's not going to be feasible for an applicator to be applying a fixed zone within the yellow and then change just for one cell in black and then change back to yellow, right? That is probably not feasible sometimes because maybe the equipment swath is going to be larger than 10 meters. And if you remember, the cell size is 10 meters. Perhaps also just the hydraulics and the mechanics of the equipment is not going to be able to change from one rate to the next, and then again, so close in space without having a lot of difference. So without having a larger chunk of cells of one color, it's going to be very hard to be applying a rate, and then for the next 10 meters, change the rate very quickly just for 10 meters, which is very short distance if you think of an equipment moving, and then change again to the rate that was originally. So this spackling effect here, we want to clean that up. We want to make these zones mostly homogeneous within the zones, although we still have two separate zones. So that's what we're going to be doing next. So, yeah. Mhm. No, I mean, you mean the colors are the same as mine? Yeah, that's okay. I mean, it could be both ways. It could be the colors like mine or flipped. And that again is just because the random selection of the starting points in k-means can lead to that. Yeah, but that's not a problem. All right, so we're going to be using a smoothing focal window. What is that? If you run the chunk below, this basically explains what is a smoothing focal window. So there's different ways of calling this. So a smoothing operator, or maybe a focal window, a focal filter, different ways of referring to the same thing. But basically, the goal of a focal window is that we first determine the size of the window. In this case here, you see this larger outer boundary of yellow here. That is what the focal window is in this case. And that has 3 columns and 3 rows. So this is a 3 by 3 focal window. That's what determines the size, is how many cells the window will consider as it applies a given function. And so we determine the size of the window, and then we need to determine a function that will be applied to the window. So in this case here, the function being applied, I believe, is the minimum. So what is happening here? The pixel in the middle of the focal window is the one which value is going to change. So that value that right now is 8 is going to change to whatever is the minimum value, and that is the function that's been applied to this window is the minimum. So because we're applying the minimum value, the minimum function, the focal window will look for the minimum value within the window. So be within 3 by 3 matrix, which in this case, if you look at all these 9 cells, the minimum value is 0, and assigns that value to that focal cell. So if you move over here, you're going to realize that this cell, which is the same cell as where it was originally 8, this cell has become 0 because it looked into all those cells within the window, it searched for the specific function, in this case, the minimum value. It found the minimum value within the window and assigned that value to your focal cell. Once it does that, it moves one step to one direction. So in this case here, let's imagine that this whole window would move one step to the right. So it would basically start at 2, 8, 14, and then go 14, 15, 16. So it would include this next column and will not include the first column. So imagine if you had a focal window that started at 2, 3, 4, 8, 9, 10, 14, 15, 16. If it was hovering there, and now the focal cell instead of 8 would be 9, the minimum value there would be, so 2, 3, 4, 8, 9, 10, 14, 15, 16. The minimum would be 2, right? So this cell that originally was 9 became 2. And so the focal window keeps moving, applying its function, extracting a metric, assigning that metric to the central cell, move over, and keeps doing that all the way through the imagery until it completes a final map that looks like this, where the final result is the focal window size that was applied to each cell, giving you the metric that you selected. Again, in this case here, the metric was the minimum value. It could have been the mean. It could have been the median. It could have been the maximum. It could have been the mode. So it could be different metrics that could be applied here, but in this case, it applied the minimum. So this is, by doing this, we're basically smoothing out the output, the outcome, especially if the function that we use is the mean. The mean especially is smooths out a little bit better than the other functions. But yeah, so we're basically going to apply this concept to our data to smooth out those speckles and remove them from the output, from the final management zone map. Before we do that, does anyone have any questions about this? Yes, Aman.
Now, matrix, like focal windows 3 by 3 matrix. But what if it would be 3 by 4 matrix and then there will be 2 focal cells? So then they add it?
Okay, so let me repeat the question. So Amandeep is asking here, so right now in this example, we're seeing a matrix that is 3 by 3. What if we were to do a matrix of size 3 by 4? Because then we would have two cells in the middle that would be the center cells. What would happen then? I don't know. I never tried that. I mean, you can try it. So after we develop here, and actually part of the assignment is going to ask you to play around with this. Not exactly on that way, but you're welcome to play around with whichever way you want. Yeah, but so one thing that you're going to notice is normally the focal window size is a combination of 2 odd numbers. So 3 by 3, 5 by 5, 7 by 7, and very rarely is a combination of, I mean, I don't think I've ever seen a focal window that is of an even number, like 2 by 2, 4 by 4, 6 by 6. And it gets back to your question. So does anyone have a guess why focal windows are normally odd and not even numbers? Anyone in Tifton?
Would it just be because they need a center?
Yes, exactly. Luke nailed it. So yeah, let me quickly do a drawing here just to create that understanding. So imagine that if you have, let's do a 2 by 2. Right, so two columns and 2 rows, 2 by 2. You do not have a center cell, right? And the whole idea of a focal window is to focus on that center cell and then change the value of the center cell based on some metric extracted from all the cells in the window. So any even numbered matrix will not have a center cell and therefore is not very useful for this application. All right. Okay, so we are going to basically need a raster to do this. And because the raster that gave rise to our interpolated data was coming from our grid, I'm basically going to bring the grid back again and make the or bring the boundary again and make the grid base on that. And I'm just thinking here, I think let me just make sure on your side, I know you have the right data. I'm trying to think if I have the right data on my side for the boundary. Okay, I may actually need to bring a different boundary. You're good. You're good. You don't have to worry. I'm gonna have to change my boundary here. So let me work on that very quickly. Okay, I think I fixed on my side. All right, so coming back here, we're gonna use our, make sure to load stars, and then we're gonna create that grid in a raster format, like we've been using as well. And then I left you here a couple of packages for you to load. I think you have both of them. If you don't have, maybe in case you don't have one, I would imagine is stars extra. So if you try to load it and it does not load, you just give install.packages on your side and it should work. So what we're going to be doing here is a list of steps that basically in the end will apply the focal window for us. And I want us to walk through this you know, in a good depth, just so you understand what's going on. So we're gonna call this zone S. We're gonna start off with our zone DF object. So give the assignment symbol. Let's start with zone DF. Because we're going to basically be smoothing cluster. Right now, zone DF has all of the other layers that we used, right? So it has elevation, slope, all the terrain, all the EC variables. Because we're just going to be applying this to cluster or applying the smoothing to cluster, I want to just keep only cluster. So let's give a pipe call a dplyr select and only select cluster. So if you run that, you're going to see that we just have cluster in geometry. The next thing here is I want to transform. So right now, this object, it has been this way. It's an SF object of type polygon. I want to transform this to a type point. So add a pipe there. So we're still vector to vector, but vector polygon to vector point. So we're going to use a function called st_cast and then give it quotation marks and type point right here. If you run that and you print zone S, now it looks the same, but we have points instead. So we have it's a geometry of type point. Add a pipe, go after the next comment. So now we're gonna have to do a step here that is basically taking our geometry and transforming that to an XY type of coordinates. And this is because that's what is going to be required for the actual focal window to be applied. So there's a function, I think, coming from stars extra package that is called st_sfc to xy. So it's basically just saying that we're transforming something from sfc to something xy. If you run that and we print zone S, now this has become a raster, but also the way that the coordinates are understood behind the scenes is different than just being a geometry. All right, so now we need to force this to be interpreted as an actual stars object. So give a pipe, come after the next comment. We're gonna use st_s_stars to do that. So if you run this, you print it. Now it's, I mean, it looks similar to what we had before, but we just had to make sure that it was seen as a stars object. And now, because we have a stars right now, then we're able to apply our focal window. So there is a function here that is called focal2, where it has 3 arguments we're going to change. So the first one is called W. So W is the size of your matrix. So what I want to propose here is that we give a matrix of size 5 by 5. To do that, we call the function matrix, and we need to give the arguments 1, 5, 5. So this is basically saying that we want one array of sizes 5 by 5. If I just run this function, matrix 1, 5, 5, just so you see what that looks like. If I just run that, this is what we get. It's just a matrix that has 5 columns, 5 rows. And then, as you can see, the central cell, the focal cell, is the one I'm highlighting. That's the one in the middle. This is where you could play around a little bit if you wanted. So let's say if I wanted to do a 3 by 3, this is where it would change it. And then you have the 3 by 3 with the central cell as the focus. Now, again, if we do a 2 by 2, as I just had a drawing for you, you're going to realize that 2 by 2 does not have a central cell, a central focus cell. So that's why even numbered cells don't work well for these types of operation. So let's keep 1, 5, 5 for a 5 by 5 matrix. If you get outside of the matrix argument and break code just to make it easier for you to see, this function has an argument for fun, which means what is the function you want to apply? I want to apply the function mean, but you could apply the function min for minimum, max for maximum, median for the median, and I believe others are also accepted here. And then finally, I want to change here the na.rm equals true. So if there are NAs, it will first remove them before giving us the results. So what you see, I just want to go back to our drawing here. So in this case here, NA is not equals, NA remove is not equals to true. So what that implies then is at this, whenever the central cell is a boundary cell, you don't have, so imagine if this cell, cell number 7 was the boundary, there is not a whole column to its left. So these left values here that do not exist will all be set to NA. And if you do not say na.rm equals true, if you allow the default to apply, which is na remove equals false, if you have any NA inside of your focal window, then the central point becomes NA. So that's why we're changing na.rm equals true, so that does not happen. All right, so if we run this, and then you print the object zone S, I mean, it's basically still a stars object, so it's a little bit difficult for us to really see what's going on. So let's transform this back to SF. So right now it's a stars, so it's a raster. Let's transform back to SF so we can make some plots. We're going to use ST as SF to do that. So if you run this, just see something here. So on my next step here, I have, well, I think it's worth it if I just create a plot of what this looks like for now, just so we can visualize before we keep going. So you can see why we have these extra steps here. So I'm gonna come to the next chunk here. I basically left you, well, I started with zone S, ggplot. If right now we want to plot this object zone S, right now it is an SF object. So we're gonna need to use geom_sf. So let's go ahead and do a geom_sf. And I wanna say AES. I want to say here fill equals to cluster. And then outside of AS, I want to say color equals NA. And stop right here. Don't add a plus yet. Just stop right here so we can see how this looks like right now. So right now, this is how the smoothing looks like. It may not be very clear to you, but what happened is because we're applying the function mean, imagine that, let me go back to the previous plot. So let's take one of these black cells that are right in the middle of the yellow cells. So it looks into one of those black cells and it has a number 1. And then all around it, it's surrounded by number 2s. And we're asking for the mean. So it's basically going to take the mean of all its neighboring values and assign that to that cell. That's what it's doing. Because it's taking the mean, sometimes the mean is not going to be exactly 1 or exactly 2, right? So imagine that in a 5x5 window, if you have a couple of 1s and then everything else is 2, your mean is going to be really close to 2, but it's not exactly 2. So because of that, we see this effect of like blurred a little bit on this color scale, because now we have values that are not just 1 and 2, is ranging from 1 to 2, depending on how many cells we got on that mean. So because of that, what I want to do here, if we come back to the zone S, well, first off, I want to just round this up and then continue the plot and then come back to show you more reasons of why we're doing some of these steps. So right after that STSSF, you can just add a pipe and then come all the way after the rounding comment. So basically what I want to do here is I just want to round up these values to the closest to the, so, well, I want to round them not necessarily up, but if a value is between 1 and 1.5, it will become 1. If a value is between 1.5 and 2, it will become 2. So we kind of skew them back to be just 1 or 2 in this data frame. So let's call a mutate function here. I want to call this column cluster underscore F for the first thing we're doing here is rounding up. So we're going to say round the current column of cluster. And I want to do to 0 digits. So it becomes either 1 or 2. And then add a pipe. And I want to come after here. And I want to transform this cluster, which right now it's still numeric. I want to transform it to categorical. So we're going to say mutate cluster underscore F equals to factor of cluster F. So if we run that, and now we rerun the same plot that we had initially. Huh. It did not work. Oh, okay, I'm using the wrong column. Sorry, we have to change cluster F here on the plot. That's what's going on. So it will look like something like this, where now we basically smooth out our all of those speckles have been smoothed out at this point. So one thing I want to show you now is if we bring the boundary, so just add the plus after that geom_sf and let it run through this entire code here. So what we're seeing here is, well, actually for the most part, it's not bad. I don't know, are you seeing something like this where the values are actually going outwards beyond the boundary, or are you seeing the values being inwards in relation to the boundary? Okay, it's running. Okay. Well, were were you all able to get to this point?
Can you say again the last step?
You mean on the up here or on the plot?
So I am right here.
Okay. Yeah, did it work for you?
Yeah, but I am not sure with the plot.
So
I think I missed something from the code there.
from the plot code?
Yeah.
Yeah, so I think the one thing
Yeah.
that we
Yeah,
changed,
can you please hold that?
yeah, so I changed here the cluster F,
Uh-uh.
then I added a plus as well to connect that with the rest.
Okay.
The boundary and their somebody outside the boundary.
It looks like mine. Perfect. All right, so I think what we are actually gonna be able to do here, and I'm going off of my original script just to make sure that things look nice. So right now, when I make this plot, I see that I have values that are going outwards from the boundary, at least from my boundary. And Amandeep said that that's what she's seen as well. What about,
Yeah, it looks the same for me too. It's going out of the boundary.
okay, so let's go ahead and do a ST intersection with the boundary. So that's going to basically clip the values to be only within the boundary. So add a plus here, we're going to call the function ST intersection and boundary W. And then let's plot again and see if that, okay, that fixed things. Perfect. All right, so so in the previous semester, now I cannot really understand why that was, but we needed to, so whenever we made this plot here, we would have a lot of the interpolated points would be, or a lot of the smooth zone points would be actually inward in relation to the boundary. So I had a few steps that were actually just interpolating those points to the boundary. So going outwards pretty much. But we don't have a lot of that problem here. We have a little bit on the top, a little bit on the bottom, but not really a lot. So I'm not too worried about it. So I don't think we're going to have to do these two steps that I had in the script. So we can just keep moving here. But so was everyone able to get to something similar to this? Again, perhaps your colors are flipped, but at least something that is similar to this.
I don't know why, but the part of the boundary doesn't show on my map because it says that no numeric argument for the boundary.
Did you have a plus here?
Yes. Oh no. Okay,
Yeah.
thank you.
Did that work?
Yes, thank you.
Perfect. All right. So you can see now, like comparing, well, so now that we created this, maybe let's go ahead and export this. So zone smoothed. So notice how I am naming this output. So zone smoothed underscore 5x5 underscore main. So I'm saying what's the size of the matrix, the focal window, and then what's the function that I'm applying. So if we go now on output and we just check this out, I want to open up both of them. So on the left, we have the unsmooth zones. On the right, we have the smooth using a 5x5 focal window, and the function mean. You can really see how applying that focal window helped us to decrease the speckling going on here. Perhaps, this is still something that we would perhaps have to change. But I guess just overall, we can see how that speckling was removed, right? By applying this smoothing function. All right, so now that we have smoothed our zones, and the data that we're going to be using from this point on is this zone S object, where we have basically cluster F as our the cluster that we're using here for these zones. But the smooth version is under cluster F. The cluster column here has the mean result of the focal window, so it is changing, but we have cluster F as our actual smoothed zone that we're going to be using from this point on. So now what I want to do is, so imagine that we have the zone. We have two zones, and this is how they look like in this field. Great. So what? Right? So what are these zones? Why are they different? Like, why did k-means say that there were these two zones, and how were they different from each other? So now it comes to the point that we're going to validate these zones with the same data that we used to create them. So we're going to connect back now on the same data frame, cluster ID 1 or 2, with all the variables that we gave to k-means, so we can run some analysis of variance models and understand how elevation, terrain, or all terrain variables, all OEC variables are affected by cluster. So we can say, well, cluster 1 has higher elevation than 2, cluster 2 has lower slope than cluster 1, and so on. We can put those numbers in there. So for us to do that, the first thing we have to do is to connect back the cluster information that is in the zone S object with the field information that is on the all V object that we imported to run the k-means. So we're going to do that step next right here. So let's give the assignment symbol. We're going to start with zone_S, give a pipe. We're going to call a function stJoin, which is when we do a spatial join, we're going to use stJoin. We're joining zone S with all_V. The join is going to be equal to st_equals. Just the word, don't add the parentheses there. And we're going to say left equals true. So if you run that, and let's just print zone S. So zone S on my side, I have 4,163 rows. Just to double check to see if things are kind of matching what we would expect. So zone S, I have 4,163. All V, I have 4,046. So I have a little bit of fewer rows on all V for some reason that I'm actually not completely sure why, because they should match. Do they match on your side? Does your zone S and all V have the same number of rows?
Mine are different.
Different? By how much?
About 100.
Okay. Huh. I'm wondering if maybe, no, this is maybe, yeah, I'm not sure. I'm not sure why exactly, but they're not, what I'm guessing is probably these, at least on my side, I think these values here that are missing from there and from the from that corner and from the bottom are probably the 100 cells that are missing. So I'm not going to be too worried about them, but. All right, so once we do the join and you print zone SDF, we have a lot of data here, right? So the standardized yield for 17, 19, 20, mean pixel, SC pixel, CV pixel, ST class, elevation, slope, aspect, flow direction, and so on. So I do want to propose that we So we remove flow direction and aspect from this data frame that we're gonna do the validation, just because we actually did not use those columns for the clustering for reasons that we already discussed about, that they're just difficult to interpret in terms of how do they impact a zone, since flow direction is numerical, but really is just a different cardinal direction. And aspect is a degree in that goes from 0 to 360. So they're really a little bit more difficult to interpret. So I just want to keep them out by doing a dplyr select minus flow dir minus aspect. So if we run that, we should end up here with 15 fields. And how many rows you would have on your side, it's going to be a little bit different than mine. If we check for the summary here again, just to make sure, again, we have clusters going from 1 and 2. This is how many cells we have in each one of the clusters. And then we just have, I have actually a lot of NAs here.
Me too.
So maybe the step that I thought we didn't need to do is actually what makes a difference. And maybe that's why I did them in the first place. And I thought I didn't need today. So let's try that, because other than that, I was not expecting to see all this the way it's going. So come back here to this chunk where we did the zone S. And we skipped here the interpolating to field boundary and the transforming from raster to vector. We skipped those. So let's come back here and do those steps. And I think that's what's going to fix our problem. And I was just not realizing that. Okay, so the interpolating to fill the boundary. So I'm having a hard time here because when we made the plot, so I'm just gonna stop the pipe here and create this and plot it again, just stopping right there. When we made this plot, it was just cluster at that point. Let me add the boundary and stop at the boundary. We did not have, so it was actually going outwards. So I wonder if something changed since last time I taught this to now, because this is not exactly the output we were getting. So I think maybe something must have happened. But anyways, let's go ahead and try to interpolate using the grid and see if perhaps that helps to solve the issue here. So if you let that pipe flow, you come after that interpolating to field boundary. We're going to use the function gstat, where we have a formula that's going to be cluster tilde 1. We give it a comma, and the data is just equals to dot, which is whatever is coming from above. Although right now this is an SF object, so I think it should be raster, but let's try to run. That's the beauty of it. We can just run and check. Well, so the gstat did not give us any complaints. Let's go ahead and try to add a pipe here. And we're gonna ask for a predict, right? So we do predict. The gstat object is already coming through the pipe, so we just have to say grid underscore R. Let's see if that's gonna work. Okay, so it did say that it worked. So no problems here. Now let's give a pipe. Well, yeah, let's give a pipe and transform this back to vector. So st underscore s underscore sf. Now, if we stop right here, let me just show you until this st has sf. if we have a var1 pred and a var1 var column, right? So we don't have a cluster column anymore. So here on the rounding, we can say cluster F equals the round of var1 pred, because that's how it's called right now. So I think that should work. Let's try to go ahead and do that. Okay, so now I do have the correct number of cells that I was expecting. So 4,046. And I want to check the summary here of zone S. Or no, not zone S. Zone S is just a smooth version. So none of that. But here, cluster underscore F. Let me run this and see how that looks like. Okay, yeah, I think this is actually what it was supposed to look like. So maybe we really needed to do that interpolation to make things work. Before I just give you all a moment to see if you're all with me, let me just run this chunk again and see if things were. Okay, so now I do have the actual data correctly. Okay, yeah, so we did need that step that I thought we could skip for today. So let me just recap. We needed to basically, after applying the focal function, we needed to interpolate to filter the boundary. So we use the gstat and predict right here. So if you remember in the past, we have used gstat as one object and then use that object into the next step, which was the predict. Here we just did that in a pipe flow. So we did not have to save intermediate products. And then at that point, it was a raster. We transformed to SF. And then everything else was the same after that point. I know that I went back and forth a few times and I coded here and there. So I just want to take a quick moment and check if anyone needs help with code. If I confuse you that you need some help.
Now mine doesn't work, and I put all the pipes because you said that it doesn't find the cluster.
So maybe take a look on this line here, Benedetta, because originally I had cluster F equals round of cluster, but now because it's coming out of predict on the interpolation, we don't have a cluster column at that point. We just have a var1 pred. Maybe check that you change this value here.
Doesn't. Oh yeah, now it works. Thank you.
Perfect. And really, like, of course, if you run this and it does not give you any errors, then it may have worked. But I guess make sure you run the following chunk and to see if your plot looks like what you would expect. And then export it. And then also do the zone SDF to join both your field data with the zones. And if you check the summary, you should be able to see. So we have NAs on var1 var. And that's pretty much it. We shouldn't have any more NAs. Well, I think
have them everywhere still.
Sorry, can you say that again?
I have them almost everywhere still.
NAs everywhere.
Almost.
Okay. Did you, let's see, what could have happened? Do you also have NAs everywhere? No, it worked for you?
I also have the NAs for the first rows.
So, you mean like when you print zone SDF, you have NAs?
The summary.
The summary. So on the summary, I was expecting for us to see NAs on var1 var and some NAs in some other places, like, but not everything NA like before. So
Yeah.
you're seeing NAs everywhere?
Yeah, it worked. It worked. I only see them on var1.var.
Yeah,
Yeah.
that's okay.
Yeah.
Yeah, what about other people in Tifton and Kiathi?
For me, it's fine.
I have everything in the summary, but I see like 5 NAs on the top, SY17, SY19.
So you mean like for,
Like 1 to 5 are NAs, and I have values for 6, 7, 8, and 9, and 10 are NAs.
but when you,
But I have all the values in the summary.
okay. What about others in Tifton?
Mine looks fine, what you have on screen.
Okay,
Same.
perfect. All right, yeah, so I guess I'm sorry that I created some confusion here. I thought that we could skip a step, but I should have just followed what I initially planned, which was to do the interpolation here to the same grid. So we matched our final product. Okay, so now that we solved that, well, I think, let's see, our next step was going to be to make some box plots. So maybe let's go until 3:30, so 3 more minutes, and then I'll give you a 5-minute break, and then we'll come back until 4. So what I'm doing here is starting with this object, zone SDF. I am removing out ST class and then pivoting longer from elevation to ECA 90. Let me just check here. So we have ECA or elevation actually is where we're starting. So elevation, starting elevation. So elevation, slope, ECA 30 and ECA 90. So pivoting longer on those columns. And then I'm just making box plots with the cluster ID 1 or 2 in the x-axis, and then that variable value on the y-axis, doing a facet wrap on each one of those 4 columns, and then adding this new geom here that I don't think you've seen yet, but it's called stat compare means, or basically just adding a p-value to test if that comparison between cluster 1 and 2 is different for different variables. So if you just go ahead and run this, let's see. This is what we get. So we get 4 different plots. We see that the p-value for all of them is highly significant. So the difference across all variables are significant. And at least on my side, again, this may be different on your side, but on my side, I'm seeing that basically cluster number 2 has higher EC shallow, higher EC deep, higher elevation, and higher slope as well. That's how I am seeing on my side. If your colors were flipped, maybe you're just seeing the flipped results. Maybe your cluster 1 has everything higher than 2. So if we looking at these box plots, and if you remember what we talked when we did already the validation of the zones themselves, or not the zones, but when we did the validation previously on the high and low stable classes on the previous exercise, which cluster here, at least looking on my screen, maybe on yours is flipped because of the colors being different, but looking at my screen, if you had to guess, which cluster would you think would be the high yielding and which one would be low yielding?
Cluster 2.
Cluster 2 looks like perhaps is the higher yielding, right? Especially when we look in space, when we look at this plot here, we know that we were seeing some higher yield levels on the left side and some lower on the right side. right? But then now we're basically trying to give a name to those clusters. Instead of saying zone 1 and zone 2, I want to say a high yield zone and a low yield zone, or perhaps, using this, we can say, well, zone 2 or management zone 2 has higher EC shallow and deep, higher elevation, and also higher slope, slightly higher slope, right? So we can basically characterize those zones. And instead of just calling 1 and 2, we can say, well, this is how they are different. This is why they are different as well. Okay, so we have these two clusters that are significantly different based on the variables that we just created to use them. Now, the next step after I give you a break is going to be for us to come back here and basically run these clusters, but comparing them to our yield stability classes instead. That's going to be our next step here. So to validate, we just validated them with the variables that we used to create them, right? So we use all these terrain and EC variables to create the management zones. We just validated them with those variables. Now I want to bring variables that the k-means algorithm did not see, which are the yield variables, and see how yield stability zones are related to these two clusters and management zones. All right, let me give you a 5-minute break here. And then once you come back, we're going to do that part of the exercise. All right, so our 5 minutes are done. Let's keep going here. So again, we just checked our clusters in relation to the few variables that we used to create them. But now I want to compare them with the standardized yield, both that in itself, but also with the classes that we created. So I basically left you all the code there. You just have to basically run it. If you're curious about what is happening in the code, what is going on in each step, you can just add a comment to any of the pipes and run until that point and see what's going on, and then let that pipe go, keep going each line. But basically now I'm pivoting longer on the standardized yield for 17, 19, and 20 and making a plot for that. So basically now we have the standardized yield of all 3 years separately and a p-value for the comparison between cluster 1 and 2. We see the p-value is highly significant, so we have a difference here between cluster, in my case, cluster 2 being higher yielding than cluster 1 across all 3 years. So this gives us an indication of yield potential, right? So maybe here yield is going to be higher on cluster 2 than cluster 1. Then, if you remember, we use the standardized yield across each individual year to calculate the mean and the CV for that standardized yield that then we use to create the classes. So on the next chunk here, I want to basically do the same plot with clusters on the x-axis, but then on the y-axis, I want the mean and the CV of yield across those 3 years, which is going to happen on this next chunk here. So we have mean pixel and CV pixel in our y-axis. So if you run that, this is what I see. So on my side, cluster 2 has lower coefficient of variation and has a higher mean pixel yield, standardized yield across 3 years. So this is all helping us to give some context to what are these clusters, how are they different in soil variables that we use to create them, right? So we gave soil variables to k-means, therefore we wanted to validate them and understand how are they different in those variables, since k-means told us that there were 2 groups. So we first validated using the soil variables themselves, and then we validated using the yield data, not the absolute yield data, right? This is not pounds of lint per acre, but we use the yield data on a relativized way, that it was both the standardized yield for each one of the years and the mean and the CV of each one of those pixels across the 3 years as well. And at least on my side, it seems like cluster number, let's see, I have cluster ... has higher CV and lower yield. In my case, the cluster that has higher CV and lower yield is cluster 1. So I'm going to write down here. And the cluster that has lower CV and greater yield is cluster 2. This needs to be according to your data, right? So this sentence here, because that's how we're going to export in a coming chunk. So make sure that this matches what you're seeing on your side. So if you have this flipped, then write accordingly.
Cluster 1 has low CV.
So cluster 1 in my case has higher CV and lower mean. All right, so something else that I want to do here, and I left you all the code, and again, you're welcome to break down this code on your side if you want. We've already done all these operations before, perhaps just not all together in the same, but I'm grouping by ST class, so the classes of spatial temporal stability, getting the total number of observations, within each one of those classes. Then I'm furthering grouping by cluster in ST class and being able to calculate the proportion of cells within each cluster that belong to different stability classes. And then making a plot here. I'm just going to run this whole thing so you can see the output. But this is what it would look like. So of all the cells that were classified as high stable, 97% of them were cluster 2. Of all the cells that were low stable, 98% of them were cluster 1. And then medium stable had a mix here, with cluster 2 still being higher than 1, but more of a mix. And then unstable areas, we have more cluster 1 inside of unstable areas. But then we have some NA values that are also here. And this is just showing in a plot with a bar plot, just to show us the proportion of that intersection between spatial temporal classes and cluster. So again, we see that cluster 2 in my case is mostly within the high stable class. Cluster 1 is mostly within the low stable class. So cluster 2 being high, cluster 1 in my case being low. And then we had a mix of both 1 and 2 between the medium stable and the unstable as well. So given all this, instead of continuing calling them cluster 1 or 2, I want to call them something more specific, something more informative. In my case, I'm going to call cluster 2 as high yielding and cluster 1 as low yielding, based on the validation that we did, right? So we went from a number like this cluster or zone 1 and 2 to actually giving them a name that informs what they represent. So we saw here the cluster 2 in my case, cluster 2 has higher yielding potential than cluster 1 and also has higher EC shallow, EC deep, higher elevation, and higher slope as well. So basically that's what we're able to tell from this validation exercise. On your side, perhaps it was flipped. Perhaps cluster 1 was the high stable or majority high stable, and cluster 2 was a majority low stable. Make sure you code that accordingly, and especially in the next chunk, which is when we're going to export. So now we want to export these clusters to file. And for that, we want to create, before we export it, I do want to create a column here. So let's give a pipe. I want to create a mutate here because I want to create a column called zone. So here I basically want to say if my cluster F equals to 1, then it's a low yield zone. And if my cluster F equals to 2, it's a high yield zone. We could use a case when here if we wanted. Because we only have 2 conditions, so it's just either this or that, just 2 conditions, we can also use an if else, which is going to be perhaps a little bit simpler when you have only 2 conditions. If you have more than 2 conditions, case when is what you need. So let's call here an if else. So if I just print zone SDF to look into the column names, I'm looking into column name. Where is it? Cluster F, right? So if else cluster F equals to quotation marks 1, give it a comma, then you say what happens to zone. What is the value the zone gets? So in my case, if cluster F equals to 1, then this is a low. I want to call this low. So low yield. So this is the name I want to give it. And then after the comma, basically you give the value of what happens if the condition does not meet, is not met. So if cluster F equals to 1, then zone becomes low. And if it's different than 1, then zone becomes high. So we have low and high, meaning low and high yield potential. If you run this, and that is already printing for you the result, and you go all the way to the bottom to see that last column, you have this new column here called zone that is going to say either low or high, depending on the zone number or cluster number that we identified above. Again, this is where that would make a difference for you. If you had it flipped, you either need to say high and then low, or you need to change 1 to 2 to make sure that it matches what you see on your side. After we do all this, we're good to export it. So let's give it a pipe. We're going to export as a write_sf. Let's give the path here. So outside of code, we go inside of data. I want to call this zone_s.geojson. And always we're going to use delete_dsn equals true. So if you run that, you should then see on your data folder, you should have the zone_s GeoJSON. All right, any questions at this point? Okay, so I'm going to keep going here. Just a quick summary of what we finished today. So in this whole exercise, we learned about the k-means algorithm. It is a clustering algorithm that we use to create groups or clusters, or in the case of Precision Ag, management zones. We found the best K for our data set, which happened to be 2. So our data set was optimized when we created 2 groups with k-means. So we went ahead and created those zones and those groups. We then explored the main drivers and main differentiators of those 2 zones using the same soil variables that we used to create the zones themselves. So we did some validation. And then we also validated the zones with the yield, spatial, temporal stability areas and the variables associated with that. And then understood the main yield stability drivers, right? So we were able to see here what was driving those zones, but also how were they responding when it came to yield. So 2 different layers of information, right? So we created the zones first based on soil variables, and then we matched them with the zones that came from the yield stability exercise and understood how they match each other. So now on our next exercise, which is going to be on Thursday, we're basically our next step is going to be to use this layer to create a variable rate prescription of something. And that's something, that input is you're going to learn next class what that's going to be. But basically that's going to be our next step here, is to, now that we have the zones and that we know that what are the soil variables driving these zones, but also what's the yield potential of these zones, we're going to use that information to determine a variable rate prescription, or to create a variable rate prescription for an input that is based on yield goal. So that's going to be our next exercise. And then lastly, I have an assignment for you. So if you copy or download our GitHub material, let me pull that up on my side here to show you. So in our GitHub material, I uploaded a assignment 8 called focal filter. So this assignment here basically is going to ask you to use the class script to change the size of the focal window and the function that you use in the focal window, and that you create figures, a PNG that you export to file for each one of the cases I'm asking you to create. And all that you do on the class script. You're not on the assignment script. On the assignment script itself, you're going to basically bring in those PNGs that you exported from the class script, bring them in here, and then have them all side by side, look at them, and answer some questions to me. So in class, we did the unsmoothed zone, and we did the smoothed 5 by 5 using the mean function. Now I'm asking you to use a different size of window, so 3 by 3, and to give me here the mean, the minimum, and the maximum functions for that window size. Make sure that you follow all the instructions here. I'm not going to walk through all of them, but make sure you read it. And then on this script here, so right now it is on GitHub, but I want you to move this into the folder of the class of the project that we just created or that we just finished that exercise. So let me actually do that. Yeah, so let me move this script there just so I can show you something that you'll be asked to complete. So you copy this from GitHub, you paste this script in the code folder of your 11 management zone. So once you create the figures I'm asking you to create, on the assignment file itself, the only coding you're going to do is to bring in those figures. And this is how you're going to do it. So I left you already the structure for you to do it. Every time you want to bring in a figure into a Quarto file, this is the way that you will write that. Exclamation point, open and closing bracket, and open and close parentheses. And in between the parentheses, you're going to type the path to the figure. So right now I am in the code folder, // I go to output, and then I select the figure. The first one I want you to bring is the unsmoothed, which is the one we did in class. So it's going to show up like this. You're also going to bring here the smoothed 5 by 5 mean, which is the one that we also did in class. But then as part of this exercise, I'm asking you to create, let's see, 3 more or 2 more? 3 more. Okay, so actually you don't need 4, you just need 3 here. So to create those other 3 and bring them here the same way, and after that's all done, then you're going to answer the questions here. Once you render it, I just want to basically copy and paste the same figure so you can see how that will look like once you render. So once you have all that and you have your answers and you render this, it's going to look like this. So you can really see all them side by side. Right now, I'm just copying and pasting the same one 4 times. But you're going to see each one of these plots will be a different plot or a different map. And then you can answer the questions here and tell me what differences do you see and which one would you choose. All right, any questions about the assignment or the class? All right, I don't hear anything. So this assignment is due in a week. You have until April 1st to conclude it. You're going to submit it on EOC. And let me open here so you can claim your attendance. All right, so I just opened the GitHub issue. Please make sure you claim your attendance. And then I'm going to stick around for a couple of minutes in case anyone has questions. And if not, then I'll see you on Thursday.